Good day, I'm Norman Wildberger. Today we're going to start having a look at this important but somewhat delicate notion of a sequence. What do we mean in mathematics by a sequence? Of course, in daily life this is a familiar word. A sequence of events in our day, for example, we might get up, brush our teeth, get dressed, have breakfast, read the paper, catch the bus, start work, and so on. So a definition of it in English might be that it's a following of one thing after another. That's one internet definition. Here's another one: a particular order in which related things follow another. So we have this intuitive English idea from daily life. We want to now transfer that to concise, clear mathematics. So in mathematics, the term sequence is related to a bunch of other concepts which are closely connected, overlapping perhaps sometimes. These are notions of a list, a set, or maybe a multiset, a vector, polynumber, ordered set, matrix, function, relation. There's some kind of similarity between all of these. These are all attempts to try to organize mathematical objects. Not just single mathematical objects, but a number of mathematical objects into some kind of larger, coherent entity, which we can then manipulate as a new mathematical object. It's a very natural and useful thing to be able to do. Nevertheless, it can be somewhat problematic to do this clearly. In the Math Foundations 42 lecture, I talked about the difficulties in defining precisely what we mean by a function. And the difficulties that are there are also in evidence for a lot of these other concepts, including the idea of a sequence. We'll see that in particular there's a big divide between dealing with so-called finite sequences and so-called infinite sequences. These are parallel, but they're quite a different kettle of fish, and we have to approach things delicately. We have to be prepared to think quite differently about finite sequences and infinite sequences. So today we're going to start with finite sequences. To focus the ideas with sequences, let's at first at least start with the simplest, perhaps most natural kinds of sequences in mathematics, which are sequences of natural numbers. So for example, here's a sequence: 1, 2, 3, 4, 5. It consists of 5 natural numbers in a certain order, and we can see that they're separated by commas. Here's another sequence called T, sequence 1, 3, 5, 7, 9, 11, 13. Here's another sequence, U, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So these are sequences that are finite. There's only a certain number of them, and then the sequence ends. However, we often want to deal with sequences which go on, which carry on according to some pattern. For example, here's a sequence, let's call it V. 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, and then it carries on in some fashion or another. And the 3 dots represent this idea that it carries on, but the 3 dots really don't tell us what the pattern is. Although you're probably pretty confident that you can guess what the pattern is, because there seems to be something going on here. Here's another very familiar sequence: 2, 3, 5, 7, 11, 13, 17, 19, and so on, which you will all recognize as the sequence of prime numbers, or at least it appears to be the sequence of prime numbers. Okay, so there's a big division between these finite sequences, these first 3, and these 2 sequences here, which are not finite. They kind of carry on, or at least we're pretending that they're carrying on by putting 3 dots. So what exactly is going on here, what exactly we're talking about, this has to be clarified. But clearly it's easier to at least start with finite sequences. So let's have a look at finite sequences of natural numbers. And we're going to do that in sort of stages, or in steps, starting with a very simple idea of a one sequence. So a one sequence of natural numbers is just a natural number. And a k plus 1 sequence is an expression of the form s sub k comma n, where s sub k is a k sequence and n is a natural number. In other words, what we're doing is we're defining, first of all, a 1 sequence, and then a 2 sequence, and then a 3 sequence, and then a 4 sequence, and so on. And what we're saying here is that, for example, a 2 sequence is what you get when you start with a 1 sequence and add a comma and another natural number. A 3 sequence is something that you get when you start with a 2 sequence, add a comma, and then another natural number. In fact, for any k, a k plus 1 sequence is obtained by adding a comma and one more natural number to a k sequence. So this is an inductive definition of sequences in the sense that we're defining them sort of one step at a time. This makes it reasonably clear how to build them up, starting from the simplest such sequences, which are just natural numbers. Having done that, we can now define a sequence S of natural numbers to be a k sequence of natural numbers for some k, a natural number. The number k is the length of the sequence, and we'll use this notation. So now we're including all the different k sequences for k equals 1, k equals 2, k equals 3, and so on, into this broader type of just a sequence, or a natural number sequence, if you like. We might introduce a new type for that kind of thing, nat sequence for natural number sequence. So for example, s equals 3, that's a 1 sequence. So it's a sequence, and its length is 1. T equals 4, 4, 27, it's a 3 sequence. Its length is 3. U equals 5, 3, 2, 1 is a 4 sequence. Its length is 4. These are all examples of natural number sequences. So the reason why we didn't proceed and say a sequence is just a bunch of natural numbers put together, separated by commas, is because we have to use this word bunch of, or some equivalent word, which essentially means the same thing as sequence. So we can say, well, a sequence is a list of numbers separated by commas, or a sequence is a succession of numbers separated by commas, or we could try to use some other word, but ultimately we're just replacing one word with another one which is pretty well equivalent to it. It's a little bit circular. So by doing this inductive definition approach, it's a little bit clearer that we're just building up sequences as objects created from smaller sequences by adding commas and more natural numbers. Let's actually introduce a closely related but slightly different notion, the idea of a list. So a list L, and we're going to be sticking with natural numbers for now, so a list of natural numbers is a sequence S of natural numbers enclosed in square brackets. So we're going to make the convention that if we take a sequence and we put it in square brackets, like here or here, then we get a list. So a list is just a sequence enclosed in square brackets. So we'll call this thing a 1 list because it's got 1 element, and we'll call this a 3 list because it's got 3 elements. The advantage in doing that is that the brackets make it clear where the list starts and stops. If we have a sequence like this on the page, it might be a little bit unclear where the sequence stops and where the next sequence begins, for example. This is a way of just being more precise about the boundaries of the object. It's very clear now that this is a separate mathematical object that we can manipulate as a separate entity. All right, so that's going to be our convention. A list is a sequence enclosed in square brackets. And we're going to use the same notation for the length of the list as we do for the length of a sequence. Let's talk a little bit about the important idea of the specification of a sequence. We've talked a little bit about specification and definitions in Math Foundations 44. So you might have a look at that again to remind you. We said that a specification of a mathematical object is really the information required to determine a particular mathematical object. And it's useful to think about how we specify sequences. So here is a sequence, 3, 5, 7. It has 3 elements in it. It's a sequence of length 3. And here I have shown you the actual elements separated by commas. And we can check that this sequence, which is a 3 sequence, really does fulfill the requirements of the definition, because it's a 2 sequence followed by a comma and a natural number. And why is this a 2 sequence? It's a 2 sequence because this is a 1 sequence followed by a comma and a natural number. And why is this a 1 sequence? It's a 1 sequence because it is a natural number. So this is exactly what we mean by a 3 sequence. And this is the full or the true specification of that sequence. We are listing all of the elements in the right order. Now this same sequence could also be described in some alternate ways. In fact, in many, many alternate ways. Here are some of them. We could say that S is the first 3 odd primes in increasing order. That's true. These are the first 3 odd primes, and we've written them in the increasing order. Another thing we could say is that S is the first 3 odd numbers bigger than 1, also in increasing order. Yes, these are the first 3 odd numbers bigger than 1 in increasing order. Or we could say that this is also the sequence of the first 3 odd Mersenne exponents. What does that mean? Well, that refers to a prime, p, that has the property that 2 to the p minus 1 is also prime. These kind of primes are called Mersenne primes. And a prime p that has the property that 2 to the p minus 1 is prime is maybe called a Mersenne exponent. So 3 is a Mersenne exponent because 3 to the p minus 1 is 7, which is prime. 5 is a Mersenne exponent because 2 to the 5th minus 1 is 31, which is prime. And 7 is a Mersenne exponent because 2 to the 7th minus 1 is 127, which is also prime. So here we have 3 different ways of describing the same sequence. But each of these is more indirect than the actual specification. These are, in my view, more like descriptions rather than specifications. They are written in English language, and with a certain amount of knowledge or a certain amount of effort, they can be translated back into the true specification. But often some work may have to be done to do that. So I want to make a distinction here. I want to make a distinction between the actual specification of the sequence by listing the elements one by one, separated by commas, and this more vague, flexible idea of giving some kind of description of the sequence. Now, this last description is quite interesting. Let me tell you how it carries on. So this is actually sequence A000043 in Neil Sloan's famous online encyclopedia of integer sequences. So here's a little bit more of this sequence of odd Mersenne exponents: 3, 5, 7, 13, 17, 19, 31, 61, 81, 107. These are all prime numbers that have the property that 2 to the p minus 1 is also prime. So since we're going to be talking a little bit about sequences, I'm going to have some more to say about this, this very lovely resource, and I recommend that you have a look at it. Okay, easy to find on the internet, Online Encyclopedia of Integer Sequences, which has many, many beautiful sequences, tens of thousands of lovely sequences. And they've sort of been cataloged by Neil Sloan and given names and given nice descriptions, and there are often many different ways of thinking about a given sequence. So the point here is that we want to distinguish between the actual idea of specifying the sequence by listing the elements and some secondary description that may or may not easily be converted into the true specification. This is a very crucial idea that manifests itself in a number of ways in mathematics. So this is a foundational series in mathematics here. We're trying to lay out mathematics clearly and precisely. We're also trying to come to grips with the weaknesses of modern mathematics, of which there are quite a lot. And here's a very, very interesting and important point. So the idea is that a sequence is truly specified only by listing each and every one of its elements one by one in order. Because this corresponds to the actual definition of what we mean by a sequence. And up to now we're only talking about finite sequences. To try to make that clear, let's have a look at this example. Let's say that S is the sequence of prime numbers between 1,000,000 and 1,050,000 in order. Now this kind of statement is often used in modern mathematics to define some mathematical object. But I think we need to be a little bit skeptical about accepting this without some thought. This is actually not a sequence as it's presented. It's rather a description of a sequence. You do not have the sequence until you actually see the elements. So here's a mantra that you might keep in mind, sort of frame it on your wall. Show me the elements. Well, here are the elements. So I've done some work. I've gone to my computer and I've gone through these 50 numbers and I figured out which ones actually are prime. And here are the primes between 1,000,000 and 1,050,000. 1,003 is prime, 1,033 is prime, 1,037 is prime, and 1,039 is prime. And if I didn't make any mistake, there are no other primes in that interval. So here is the sequence S. Now it's written out explicitly. Now we have actually fulfilled the requirements of the definition. We can say this is a true specification of a sequence. This, well, this is, in my view, not a specification of a sequence. It's more a description of a sequence. So this illustrates the difference between a specification, like this, and a description like this. The specification is precise and fulfills exactly the requirements of the definition, while a description has a certain vagueness to it, or may have a certain vagueness to it. There's rather a range of possibilities for a description. Description might be very, very clear, or it might be very, very unclear. It may be very easy to come up with the sequence from a description. It may be very, very hard to come up with a sequence from the description. Specifications versus description. There's a big conceptual difference between these two, and I want you to keep this in mind. Let's have a look at another example. Here is another sequence which has the same form as the previous example. The sequence of all prime numbers between 10 to the 10 to the 6th and 10 to the 10 to the 6th plus 50 to the 6th. It has the same kind of form, it's just that the numbers are bigger than they were in the previous example. So we're supposed to take these primes and put them in order, and that's a sequence. But this is a blue sky definition. So this is very challenging to find all the prime numbers in this range, and very possibly, maybe we'll never know if there are any such primes. Depends on how big our computing facilities get. So is this a definition? Is this really a specification, or are we just talking about some fairy tale object here? This is the kind of question that should pop into your mind when you see a definition like this, a so-called definition or specification. Here's another example. Consider the sequence of integers from 1 up to 10 to the 9, or a billion. All right, well, this is a pretty explicit sequence. 1, 2, 3, 4, 5, 6, and so on up to 1 billion. A billion is a big number, but it's not a number that we don't deal with in economics and so on. So, is this a sequence? Is this a specification of a sequence? Have I listed all the elements in this sequence? Well, clearly I haven't, because instead of the numbers 7, 8, 9, and up to the one less than this, I've substituted these 3 little dots. So I've clearly left out something, but on the other hand, what I've left out is pretty clear. We all could at least make an attempt at filling these things in. It might take us some years to do so. So my feeling about this is, well, it's borderline. This is pretty decent specification, but you could make some objection to this as a specification of a sequence. That becomes clearer when we up the ante a little bit. Here's a similar kind of thing, the sequence of integers, now from n equals 1 up to 10 to the 10 to the 9. Not 10 to the 9, but 10 to the 10 to the 9. That's so much bigger than 10 to the 9, there's no hope of being able to list all these numbers in a real sequence. It's absolutely impossible with current technology, and even technology in the next few thousands of years. But still, it's something very unambiguous about what this sequence is. Well, we think it's reasonably unambiguous, but maybe if we actually had to think about it, we might be a little bit not so sure. Because these numbers are starting to get pretty big. And if we up the ante even more, if we go from 1 up to 10 to the 10 to the 10 to the 9, which is vastly bigger than this one, then our dismay ought to increase a little bit. We ought to be becoming more and more nervous about claims about all the numbers between 1 and this number here. Probably the universe has a hard time trying to fit all these numbers into it. Does it make sense to talk about a sequence if there's not enough room in the universe to actually write it down, even theoretically? We're starting to get to some philosophical one-hand clapping kind of questions here. And basically, I'm not really interested in having philosophical questions in mathematics, so I think we need to treat such objects with some care. We need to have some respect for very, very big numbers, and we're going to be talking more about very, very big numbers, much bigger than these ones, in future videos. In this lecture, we've only been talking about sequences of natural numbers, but of course, we can easily extend this to sequences of other kinds of things like rational numbers, which is particularly interesting for us when we're doing analysis. So a sequence of rational numbers can be defined in a similar kind of way. First, we can define what we mean by a k-sequence of rational numbers, starting with k equals 1, then k equals 2, then k equals 3, and so on inductively. So for example, this would be a 4 sequence of rational numbers. 3 halves, comma, minus a half, comma, 0, comma, 4/3. And then we can define a sequence of rational numbers just to be a k-sequence for some natural number k. All right, so such finite sequences, whether they're natural numbers or rational numbers, are interesting, but ultimately we want to go further. What we really would like to do is to consider infinite sequences, because most of the sequences that sort of naturally pop up have this unending aspect. They don't just carry on and stop, they want to keep going. And we want to study these kinds of things in mathematics. The question is, how are we going to do that? How are we going to have a logical, clear approach to things that go on and on forever, like, for example, the basic sequence of natural numbers, 1, 2, 3, 4, 5, 6. So next time, for example, we're going to be looking at some infinite sequences. For example, this one, A40 in Sloan's Encyclopedia, which is familiar, I hope. And it seems to carry on, but actually does it keep on going forever? It's a bit of a question. Maybe it's a semi-philosophical question, but we're going to have a little think about that kind of issue next time. So infinite sequences, how do we approach them? I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.